Okay, so in this chapter we'll talk about simulation. Probably the most important question to answer right off the bat is, what do you actually care about when you're simulating? And so that helps us find the correct level of abstraction. Do we care about the electromagnetic properties? We have an actual motor that has an axle that's spinning, and it spins in relation to an electromagnetic field that's produced when you connect the backside of the motor to a battery. Is it important for us to simulate those electromagnetic properties for what we're trying to solve in our class? I would say it depends much on what we're trying to optimize or what we're trying to explore. If we're just looking to see if our kinematics work correctly, we don't really need to care about having our model at this level of detail. Likewise, our robot itself while it's driving around, if you tell it to go 5 centimeters per second, if we were to look at the actual plot of its speed, it would ramp up and get to 5 centimeters per second. But it's not going to do so instantaneously. Do we need to care about the amount of time it takes to ramp up to the speed that we care about? Sometimes we probably do. For the most part, in this class with our simple mobile robots, it's just not that high of stakes. We don't care to model things like inertia. Similarly, our robot actually will behave a little bit more differently over time. So if we go back to our motor here, it's not just the electromagnetic properties, it's also how this motor, how fast it responds to commands as the battery capacity changes. You probably haven't seen that be much of a problem this semester, because we're pretty much always making sure that that battery is running above 3.5 volts. And the performance of the robot will pretty much be the same as long as that battery doesn't go below that value. So that's probably also something that we don't need to simulate. We're just not going to model that. Do we care about noise? So things like sensor noise or actuation noise, which can come in the form of wheel slippage. And here's where we start getting into questions that actually it matters what we're trying to do. If we're just looking at things like our kinematic model, we probably don't need to care about wheel slippage. However, if we want to start incorporating our compass using sensor fusion, then we probably do want to model some sort of noise, both on the sensor level and with the robot's interaction with the world. On the other hand, do we need to model it as wheel slippage? Do we really care if it's wheel slippage versus some other kind of disturbance, like a lump in the carpet? Probably not. So we can just do that. We can simulate that by just adding some noise from a random normal distribution with mean of mu and a given standard deviation. We don't necessarily care, like I said, I'll just reiterate, if it's from the wheels or if it's from some other imperfections in the robot's setup. Are the wheels wobbling? Are they slipping? Is the carpet uneven? At some point, that will become important if we're trying to prevent certain types of noise or inaccuracies, but we're not going to get to that point in this class. So when we talk about simulation, we can really start with the simplest version, called an analytical model, also sometimes called a closed-form solution. And I'll start by just saying sometimes this doesn't exist. So whenever your simulation gets more complicated, let's say you do care about sensor noise or you do care about wheel slippage, you're not going to have an analytical model for that type of scenario. Something that tells you from a single invocation of a function what the change in configuration might be. But if we're looking at this simple little robot here, which just operates in this one-dimensional plane, line, I guess, then we can get away with this really simple closed-form solution. So at time t, where is the robot's x position? Maybe I'll define that to be the center of mass here for the chassis. So maybe we'll mark this as x is equal to 0. We'll just say that that's the 0 point for our inertial frame, our coordinate frame. Where is this robot at time, so that's at x0. Where is the robot at time t is equal to, for example, 5 seconds? Well, if we assume that our wheel rotates, or both wheels rotate, at a specific fixed angular velocity of omega, and we know the radius of the wheels, and we know how much long we want it to run, so for example that's 5 seconds in this scenario, and on our robots those are about 7 centimeters, and we get to set this. So maybe we say that the angular rate is 1 radian per second. So if we know all those quantities, and we define us as having started at x naught is equal to 0, we can compute this without having to do any more complex form of simulation. And so I can show you what that would look like. So here's a simple analytical model. And the way I wrote this little widget to work is that when I push play, in JavaScript, I constantly run a function where I just say at a given time t, what is my x location? It essentially looks like that. And I can jump backward and forward in time easily because t can be computed with just a single value like this. More specifically, I'm using this exact function here in simulation. We can say that x naught, the initial position, is just initialized to 0. We don't need to initialize a value for the chassis position because it's always going to be used or read after we call the simulate function. I can set the angular velocity. Here I just set the wheel radius to 1 just to make my life a little bit easier, not having to worry about the exact dimensions of the robot. And then in a single line of code, this can all be on a single line of code, but I broke it into two, one where we compute v and then just feed it in here, really just so it fit on the slide. We can compute the chassis position and do that for any time. So back to this little example here, if you look at the time that's given here, I just have in the background running a JavaScript timer that fires once every 60th or 60 times per second, and it just calls that function. It says, okay, the current time is 1.2 seconds. Where should the robot be? And then my rendering code just moves the robot wherever it should be in space. And so this simulation is really just calling that analytical model a bunch of times to have it go forward. And a little bit of a preview here, I can actually do things like very, very simple collision detection with this simple analytical model. So that sort of ruins my next slide here, is what if we add a wall? Can we still get away with doing this simple analytical solution? And the answer is yes. We can just check our distance to the wall at each time step. And if our distance to the wall is still greater than 0, meaning our chassis position is here, and then it gets to here, and then it gets to here, and then the distance to the wall is defined by the closest point on the chassis, so that point on the very front of it. If that distance to wall is ever less than or equal to 0, we just stop the robot moving forward. And we can still do something cute like animate that the wheels are rotating, which is why it looks like this is still doing something even after the robot hits the wall. But really, I'm just no longer changing the position of the chassis. A more interesting question is, what happens if we want dynamic control? And it's easier for me to show you what I mean by that. So looking at another widget on the same page, what happens if I want the robot to approach the wall but then slow down as it gets close? It's that slowing down motion that's really going to cause us problems with the analytical model. The equation for computing where we are at any given time becomes a lot more complicated if we're not running at a fixed speed or don't have something like a fixed wheel radius. I'd encourage you to think about what that equation might actually look like. And just to give you a hint, it would say something like, if my distance is greater than some value that gives me the maximum value for omega, so this is just capital omega to indicate it's the maximum value that I could have for my angular velocity of the wheel. So if my distance is greater than whatever value sort of clips here at omega, then I can pretty much just use this original equation as is. But as I start getting closer to the wall and I start shifting over to using this more complicated version of control, so here's my wheel speed, it now depends on d, which is the distance to the wall, and a couple of control values. So this would be distance, this would be my gain, like in a proportional gain, and this would be a proportional offset. It helps us have the robot so that it can stop some distance away from the wall, as opposed to just coming to rest directly at the wall. That's all this value for B, this bias value, is doing. So you could come up with an analytical model that solves this pretty simply. On the other hand, if I wanted to add a second wall and a third wall, or have the wall moving as well, then you basically have to completely throw this analytical solution out the window. So for the most part, nobody actually simulates using this analytical solution. It's just almost never useful in practice. So instead what we do is we use something called numerical simulation. And there's really not much of a difference between those two types. So you've got your analytical version and your numerical version. The big difference here is that if you look for your final value for your position, x of t, it depends on what are essentially constants. Those are all values that we can reasonably assume are constants. Sometimes we'll have a value for omega that's not a constant, and that's the only thing that complicates the analytical solution. On the other hand, if we look at the numerical solution, we see some values that carry over from before, and delta t is typically a constant. It's a time step, so how much time do we want to have passed at the current values for omega and omega r, essentially is how you would read that. How long have we been going at this speed? But the more interesting part here is that x of t depends on where it used to be. So the way you would read this equation is if I'm here and I am currently going at, for example, omega equals 1 with a radius of 1 and a delta t of 0.1, I know after 0.1 seconds that I am now here. So I've shifted my robot forward. However, if I am currently here, and maybe let's say this is at current time step, so I'm currently here, and let's say the current time is at 4 seconds, and I want to know where am I at time x of 4.1. Well, I can say, what's my value at x4, so at the 4-second mark, plus how fast am I going, so that's speed, and for how long for how long forward in time I'm going to run the simulation at that speed. And really, I'd move very little, but I'm just going to exaggerate this, the amount of distance between these 2 points, just so it's easier to review. So that's the distance that I've traveled. That's what I've computed. That's what I've computed just with this second-hand part. The initial position x4 is given by this, and then again the step here is given by the second-hand part. The speed and then the time. So you've got something in meters per second for the speed, multiplied by seconds, and that's going to give you distance. So there's our fancy dimensional analysis. And this format might not seem that different, but it's extremely convenient because it means I can start out at x0, compute my position at x1, 2, 3, keep stepping forward through time. It doesn't have to be fixed time steps. In fact, there are some numerical algorithms that will change the step depending on how much activity there is. I can proceed that all the way forward to 4 seconds. And more importantly, at each time step in between, I can do something like change omega. I can also change R if we really wanted to, say like the wheel is a transformable wheel, which is actually a concept related to my research area. But almost always we will be instead just changing the control, so the speed of the robot's wheels. And that's really not that much different to code up from what I showed before. So our simulate function, instead of taking a specific time, instead it's going to take a duration. And that's because every time you call simulate, it's going to start at some initial position and then step us forward through time. Now, what's not shown on this slide, just because I try to keep the code as simple as possible for the slide, is that I could be, for example, in here, changing the angular velocity. Depending upon, for example, some function of my distance to the target and my current pose, which is essentially what our position controllers are doing on the robot themselves. If you recall, we're changing the velocity of the wheels, and it depends on how close and the angle to our target, how close we are to our goal and the angle to the goal. And now would be a good time to show you what this looks like in practice. I'll show you my coding setup for how I actually code up the simulation for this class.